Hi, and welcome. This is just a series of videos that I'll be making to help reinforce some of the ideas in the class that may be a little bit more difficult. And you can also use them to review things when it's time for the exam. Now, they're not rehearsed. I'm not going to cut anything in them. There's not going to be like a bunch of special effects or anything like that. So they're kind of off the cuff, and I might get into tangents, or I might have to stop and collect my thoughts. But the one thing I will guarantee is that they all will be about chemistry, and I'll eventually get to the point that I want to make. So thanks for tuning into the video, and the first thing we'll talk about today is the periodic table and what these numbers mean. So this is the element lithium. And, obviously the symbols go for the element, and you can look up what those symbols are. Most of them match, a few of them don't. My favorite being tungsten. Its symbol is W, which is for wolfram. It's one of its sort of original names before they decided on tungsten. But again, neither here nor there, we're here to talk about lithium. So this first number 3 is the atomic number. And so what that means is that every atom of lithium has 3 protons. If you do not have 3 protons, you cannot be an atom of lithium. So if any element is identified as lithium, you can be sure that there are 3 protons. Now, in a neutral atom of lithium, of which there are very few, because the alkali metals, the group that lithium's in, are very reactive. A neutral atom of lithium, since it has 3 protons, and every atom of lithium currently on the planet right now has 3 protons, a neutral atom will also have 3 electrons. Now, when we start talking about the bonding behavior of lithium and why it does what it does, we're going to see that very few atoms of lithium actually have those 3, all 3 of the electrons. That lithium actually likes to lose one of them. But that's an idea for another time. What we need to know is that this is the atomic number, and that identifies lithium, and that corresponds to the protons. But we know that of the parts of the atom that have mass, there are protons and neutrons. And so when we look down here, this is the mass. And there's this weird kind of decimal to it. And here's the issue, is that if I was to get a big bucket of lithium atoms, and I started picking the lithium atoms out of the bucket, I would never find one that was 6.94. And the reason is because when we assign masses to protons and neutrons, even though the neutron is just a little bit bigger, just a tiny, tiny bit bigger, and you'll hear my theory on that later, but the neutron is just a tiny, tiny bit bigger, we assign them as AMU masses of 1 because it's really close. And so there's no way that you can have a decimal part of an element, and yet when you look at the periodic table, they all have decimals for the most part. Some periodic tables give oxygen as 16. I always remember that, 16.00. But I think actually the one in the book does 15.99. But why it has these decimals and it's not a whole number is that there are 2 isotopes of lithium. And an isotope has, it's lithium, so it has 3 protons, but the 2 common isotopes of lithium, I'm getting a pen here, the 2 common isotopes of lithium are lithium 6 and lithium 7. So they both have 3 protons in the nucleus. But lithium 6 would have 3 neutrons. Whereas lithium 7 would have 4 neutrons. And that's essentially what an isotope is. It is just an atom of a certain element with a different number of neutrons. And so the 6, 3 and 3 is 6. 3 and 4 is 7. I make my 7s funny. It's because my mom's from Germany, but that's okay. So 3 and 4 is 7. Now, when we look at how much lithium is present, you can see that this number is almost 7, and so that would indicate we have a lot more of the 7 isotope. And when you look it up, it is actually true. It's 92.5% lithium, and that would be 7.5% 6. So what we can do, though, with that information is we can take a weighted average, okay? And so sometimes when you do these problems, you will be given a really specific mass, and I'm going to see if I can look up the isotopes, the mass of the isotopes here really quick. Okay, so the mass of lithium 7, we're going to use really precise masses here, is 7.016 AMU, and then lithium 6 is 6.015 AMU, and that is just taking into account the fact that those neutrons just have a little bit more mass, and it'll just give us it'll give us that really nice precise answer that we want. So we're gonna do a weighted average and do that together. So there's 2 isotopes, so our average is going to have 2 parts. So if we take the mass of lithium 6, 6.015 AMU, and then we multiply it by the decimal percent. Okay, so when you take the decimal percent, you just take a percent and divide it by 100. And so essentially you take this and you move it 1, 2, because that's dividing by 100. So we're taking, 7.5 becomes 0.075. And I can tell you the one problem that a lot of people are going to have is they're going to see the 7.5 and they'll make it 0.75, and that's not 7.5. That is 75%. Don't do that. Okay, and then we're going to add that to 7.016 times 0.925. Now, since that was 92.5, divide that by 100. You do get 0.925. And I'm going to get my trusty calculator here. And I'm going to do this in 2 parts. Normally, I would just put this all in together, but 6.015. Oops. And so that gives me a big decimal, and I'm just going to write down everything my calculator gives me, and then we can deal with sig figs later. Okay, but so if I've done that first part correctly, I've got 0.451125, and all I did there was multiply this, the mass of the 6, times the decimal percent. And then I'm going to go 7.016 times 0.925, boom, and 6.4898. And so I'm just going to add those 2 numbers together, plus 0.451125 and 6.940. 0.0925. And so you see that when you take that down, that gives us the 6.94 that we have seen right here on the periodic table. And so all of those masses on the periodic table are derived doing a problem that way. Now lithium is really simple because it only has 2 isotopes. Some elements have, like 5 isotopes. And so it's still a simple problem, but it just takes a little bit more to count. And the more isotopes you have, the more likely 1 or 2 of them are going to have really small percentages, which is another easy way to screw up. But, if you don't screw up a couple of times, you don't learn.